In this ProteusDS training session, we're going to talk about fundamentals of working with ABA connections with rigid bodies. What we're going to cover is a review of rigid body and rigid body reference frames. We're going to talk about what ABA connections are all about and get into more details with reference frames, and in particular the joint reference frames. We'll talk a little bit about limitations with this and then go over an example. With rigid bodies, the key between them and a lot of the other simplified models in the software is they track both linear and orientation of a system through space. There's a rigid body reference frame, and both the linear and orientation matters and is accounted for in the motion and hydrodynamic evaluations. In larger and awkwardly shaped or complex shaped systems like this Nomad buoy hull, it's often quite handy at resolving these effects and tracking the tilt of a system in wind waves and currents. Rigid bodies, again, have 6 degrees of freedom: surge, sway, and heave are the linear degrees of freedom, and roll, pitch, and yaw are the orientation degrees of freedom. And everything is set up and configured with respects to a rigid body reference frame. The state of the rigid body is how this rigid body reference frame has moved away from the global frame. Remember that the rigid body reference frame is an arbitrary decision about where it can be configured with respect to the detail of the system. It's good practice to pick a place that's invariant to design, like the keel and baseline of a system like this Nomad buoy. As the CG might shift with respects to load out of this particular system, the rigid body reference frame doesn't need to change. So it wouldn't be the best idea to have a rigid body reference frame at the same place as the center of gravity location, because all the parameters are going to shift around when these factors change. So when it's in a location, it's easy to measure different properties. We specify things like, the connections, mooring connections, features that we're adding, the center of gravity as well. And when it comes to making articulated body joints, we want an easy way to specify where the joint connection frames are. So articulated bodies are a series of rigid bodies connected to each other with joints. The kinds of joints that are available are prismatic, which is a 1 degree of freedom linear joint, revolute, which is a 1 degree of freedom rotational joint, and these two joints, prismatic and revolute, comprise like 99% of how these kinds of connections are used in a lot of practice. But there's other joints available as well. So the cylinder joint is a 2 degree of freedom joint that allows both linear and rotational about the same axis. A planar joint is 2 linear degrees of freedom in a plane. Spherical, which is 3 degrees of rotation. Universal joint, which is 2 degrees of rotational freedom, constraining the third rotation joint. And helical joint. So we're going to look at an example with a revolute joint on our Nomad system. Again, with the rigid body reference frame on the baseline and the aft, there's a CG location somewhere X forward and Z up in the system. The mooring connection points might be connected in the back here as well. And with regards to the mooring yoke, we want to connect this second articulated rigid body system on the axle here. So we need to be able to specify a joint frame that's often some X down a little bit in Z, and that's where the joint frame that's on the master in this connection relationship between these two rigid bodies is located. The second rigid body we'd be working with would be this other rigid body, which is this mooring yoke frame. We could set it up with a rigid body frame anywhere in this frame, but in this example it's just specified right here. And then we'd also need to be able to specify the joint frame location with respect to the follower rigid body, and then the axle will be going right through this system here, through the end of the frame here. So when they're connected together, you have these two rigid bodies connected to each other. So when you're working with rigid bodies that are in an articulated body connection, you just treat the rigid bodies the same as you had before. There's still a rigid body frame. You still have to specify the CG location. You add load features just like you did before, cylinder or custom mesh or cuboids or whatever. You make connections to other D objects, maybe like cables, for example, just as you had before. One difference is that the follower rigid body in the relationship, the state vector is then replaced with the degree of freedom of the joint. So in this example here, the Nomad hull is still 6 degrees of freedom. It's set up as the master between the connection relationship, and instead of having 6 degrees of freedom for the follower yoke structure, now there's only 1 degree of freedom, and that's the revolute joint angle around this. So position and velocity of that joint angle. Note that you can hold joints completely fixed using kinematic 0 flag. Remember, the kinematic flag can be used to set up a constant velocity mode, which can also mean 0 velocity, static, if the initial velocity is set to 0. Oftentimes, it's really handy to use the visualizer in ProteusDS simulation toolbox to get an understanding of just how the system is configured. If it's configured up correctly, test the joint state and see what happens. So some limitations on working with articulated bodies: you can't do anything you want. Unfortunately, they're for serial connections. You can't make a loop of rigid body structures going back to a master. So-called tree structures are possible only. This means that you could have branching out rigid body structures out from this. Note that there is an alternative to connections between rigid bodies using force connections. And the difference between this is that a force connection uses a spring and damper at a specific location on both bodies to hold them together. Advantages and disadvantages of both of them: well, it tends to be computationally faster and more efficient to work with articulated body connections if you can. It's really nice and easy to configure a chain of rigid bodies, and it's nice to see them in pre-visualization. Rigid body force connections allow you to make loops if you need to do that. We're going to work with an example now. If you look at the input files for paddle with ABA connection, now you'll see a very simple floating frame and paddle system. So this paddle uses a cuboid of 20 meter by 20 meters by 2 meters thick with a large mass and inertia value. Don't pay too much attention to these mass values. This is configured so that basically it sits about halfway in the water. Just whatever the displacement is of that is what the mass is, and the inertia is just the same number. The frame is heavier, and you also uses a similar cuboid just for a visual reference there. So when you open up these this project file here, you'll see there's our paddle and there's our frame on the bottle, and you can see all the parameters there set up to use the same cuboid component there. Now, when we're looking at the rigid body frames, they're set up just to be in the center of the volume of these structures for simplicity. Positive Z is pointing down for both of them. And there's an ABA connection set about here, so it's a hinging paddle on this floating frame. When we set the joint connection locations for the frame and paddle, it's in the connection information. Master connection location, which is the location of the joint frame with respect to the master rigid body. And in this sense, we have the frame is set up as the master D object, and the follower is set up as the paddle D object. So master connection location for the connection is going to indicate a small negative Z location. And in fact, that's exactly what we can see here for this master connection location. There's -1 in Z, and everything else is 0. So it's just, remember this box is 2 meters tall, so it's just -1 to here. That's the joint connection for location on the master, and then the follower, remember this box is 20 meters long, so we have a 10 meters in Z lining it up here. You can see some inputs here for selecting the joint type. We're not changing these right now. Note under revolute joint, angular joint properties, we can specify things like joint stiffness and damping, end stop stiffness and damping, the offset of the joint for the end stops, and many other parameters for constant force and amplitude and frequency forces and things like that. Let's go back to our system here and just look at the paddle state. Here we are. You can see we've selected 1 degree of freedom for the inputs, and everything is set up at 0, but if I pick 45 degrees angle, you can see that it's in the visualizer, it's helping show, oh yes, okay, we've configured it up correctly. We're expecting it to see here this pivoting about this. Note that the cuboid volumes are interfering with each other. This right now, Proteus does not calculate any contact forces in between these hulls, so that wouldn't cause anything to happen. It doesn't affect the hydrodynamics as well. It's just independently calculating the hydrodynamic loads on each structure. If we go back to the state and set it to -45, you can see how it swings back the other way. Let's set this back up to vertical. If we go to the joint and space things out a little bit more, say we go to 2 and we go to 11, you'll see there's a gap between the two of them, and the system will be hinging about this point in front of it. So if we go 90 degrees on the joint, you'll see the joint is actually sort of even further up off the master rigid body. So just, playing with the inputs, and it will help you get a sense of how it's configured and how it's set up. I'm going to set this back to vertical here, and it looks like these setup files are configured to run with some waves, so you can play with the simulation and see how the system floats and moves around in the system. But I'm not going to do that right now. So we'll close this one. We have another setup file here with a paddle and frame connection, and these are set up with force connections. So the difference is, note the inputs are really, really similar. We still have master connection location. We still have follower connection location. You can activate different degrees of freedom for constraints, so only linear spring stiffness is activated right now in X, Y, and Z. It's free to rotate in about X, about Y, about Z. And there's a very large translational stiffness and damping configured for this joint. Another factor to note is you still have to directly specify the full state for both of them. So in this case, we have the paddle. You still have to position the rigid body. And the reason for this is that there's a different algorithm behind the scenes that's treating force connections versus treating rigid bodies in the articulated body algorithm system, where they're connected by these joints. So this is just looking for spring stiffness and damping between a specific location between two rigid bodies that are otherwise unrelated to each other. So just to review, we went over some review of rigid bodies and rigid body frames. We talked about the ABA connections. We talked more about reference frames with the joint connection frames. We talked a little bit about limitations and went through an example, both ABA and force connection example with rigid body. Thanks for watching.